Thank you, and thank you very much to the organizers for inviting me to this conference in honor of Gordon's birthday. I'm probably one of the speakers who has had least contact with Gordon. I think we've only met once before, 12 years ago at a conference in Oberwolfach. But I've profited a lot from his papers, especially during my PhD, the joint paper with WITEC on definitions and properties of minimal representations. And more recently, I've also looked a lot at Gordon's paper from 1990 with David Kazhdan. And in some sense, what I'm going to talk about today grew out of the problem that I didn't quite understand the paper. I didn't quite understand some construction. And that's what I'm going to tell you about today. So you could have as an undertitle my viewpoint on this paper. So here's a short outline. I'm going to talk a little bit about motivation for constructions of minimal representations, and then I'm going to present 3 explicit constructions of minimal representations. The first one is the one from Gordon and Kazhdan. The third one is my contribution, and the second one is kind of an intermediate step to understand why I'm doing the construction in the last step, the way I'm doing it. But let me start with the motivation. So the goal is to construct explicitly minimal representations, explicit models, explicit realizations of minimal representations in the Archimedean world. And usually one is interested in models which are appropriate for studying certain questions. And the type of model I want to study is what I would call an L2 model or Schrödinger model, as it appeared in the very first talk of today in Toshi's talk. And there are probably different ways of defining what an L2 model should be. Here's my take on it. You want your representation to be unitary. So you can talk about representation on a Hilbert space, and that should be the Hilbert space of L2 functions on let's say, a manifold. You can probably relax this assumption. But let's do with manifolds for now and functions on a manifold. And you want that since any 2 separable Hilbert spaces are isomorphic, you want your representation to have something to do with the geometry of the manifold. And in general, you cannot assume that your group is acting geometrically on M, because this will not produce a whole lot of examples. So you relax this assumption a little bit, and in the Archimedean world, you can say, I want that my Lie algebra is acting by differential operators on at least the smooth vectors in this representation. If it's acting by vector fields and you can integrate the vector fields, then the group is actually acting on the manifold. But in general, you want this to be a more relaxed assumption here, because if you look at kind of the prime example for an L2 realization, the metaplectic representation, then you see that the metaplectic representation can be realized in the Schrödinger model on L2 functions on Rn. And the Lie algebra action is given by differential operators of order 0, 1, and 2. So it's not given by vector fields. A few other examples. There's a paper from 1980 by Gelfand, who's writing down explicitly the Lie algebra representation of G2, which is supposed to be the minimal representation, on functions in 3 variables. And this paper, I think it's a 2 or 3 page paper, and he just states the formulas. And you can verify that it's actually a Lie algebra representation, and it actually comes from a representation on L2, although he doesn't say so much about it. So this was kind of the first magic for me. I didn't understand where these formulas come from. I didn't understand how Gelfand came up with these formulas for the minimal representation of G2. There's a similar construction by Torasot, or it's called maybe the exceptional representation of the double cover of SL3. He also makes the construction very explicit on functions in 2 variables. Actually becomes a unitary representation on the L2 functions on R2. And you can check that the Lie algebra acts by differential operators. So this is also what I would call an L2 model. And another model that appeared in the first talk of today by Toshi is this minimal representation of indefinite orthogonal groups, which can be realized on L2 functions on isotropic cone C. There's, of course, another construction. That's the one by Kazhdan-Savin, which I'm going to talk about a little later. Let me first say something about why should one care about L2 models? Why are L2 models particularly good? I think in this room there are enough people studying theta correspondence to know that for example, for the metaplectic representation, exactly this realization on L2 functions on R2 is the one that you need to study dual pair correspondences. You can also study other types of branching laws, not necessarily dual pairs, but in the Archimedean world, realizing something on L2 makes spectral theory of differential operators available, acting on L2 as self-adjoint operators. You could use Mackey theory if something's acting geometrically. So L2 models offer a certain framework that makes branching problems easier to study. There are also other applications to say automorphic forms. There's a paper by Kazhdan, Piolin, and Waldron studying theta series, where they use spherical vectors and minimal representations. That also stems from an L2 model. There is a lot of recent work on Fourier coefficients of global automorphic forms for these, where these L2 models are used to a certain extent. And then what was advocated in the very first talk today is relations to global analysis and special functions or Fourier transforms. So there's a variety of reasons why one should care about L2 models. So let's look at one construction, and that's the one by Kazhdan-Savin. So again, I'm only concerned with real groups, with the Archimedean place. So let's take a real reductive group, and let's take a split one of type D or E. So there's the three exceptional groups, and you could also take one of type D. And the construction is very elegant, and it basically builds on the existence of a parabolic subgroup, a maximal parabolic subgroup in all these groups, which is a Heisenberg, which has as unipotent radical a Heisenberg group. So it's a symplectic vector space times the center here. And I want to slightly change notation from the usual Langland's decomposition here. I want A to be disconnected to also contain R minus. So A is disconnected, has two connected components. So sometimes you take something from M and put it onto A. But that's not so crucial for the construction. Then the beginning of the construction starts with a irreducible representation of the unipotent radical of N. It's a Heisenberg group. And the Heisenberg group has unitary representations in two families, the finite dimensional characters and the infinite dimensional ones. And you pick one of the infinite dimensional ones. In some sense, it doesn't matter which one you pick. And they can all be realized in this oscillator model or Schrödinger model on L2 functions on a Lagrangian submanifold of your symplectic vector space V. And then the first claim that you have to show is that this representation can be extended to M times N. Of course, you extend by the metaplectic representation, and you have to show that this is possible for M. So either M splits in the cover, or it's possible for other methods. And then you have a representation of the group Mn. M is acting by the metaplectic representation, N by the oscillator representation of the Heisenberg group. And you can induce to the parabolic subgroup to MAN. So in some sense, you're adding an extra variable, which is A here. And that's why you choose A to be R cross. So in some sense, you add another complete real variable. And you can realize this induction in rho is realized on L2 functions on lambda. And you add one variable, so you realize on L2 functions on lambda times this variable in A. And then you want to, so that's what Kazhdan and Savin do. They extend this representation to a representation of G. And for this, they note that G is generated by this parabolic subgroup and some element of the Weyl group, which flips P to something on the opposite side, which is enough to generate the whole group. They have G generated by P and some Weyl group element. So the only thing you have to do is to define the representation on this Weyl group element in such a way that it extends to a representation of the group. And this is kind of where the magic happens, where you have to find the right formula. And this was also always something I didn't quite understand. Where does this formula come from? How can I explain this formula? But it works. They check that it works in these cases. They check the corresponding relations, and it gives a unique extension of this representation of P on an L2 space to a representation of G on this Hilbert space, and that's the minimal representation in these cases. So you have an explicit model on the L2 functions, and in some sense you describe the representation of the group, and you can also find the representation on the Lie algebra level in this way. So let me briefly explain the formula without too many details. This lambda is the variable R in R cross. X x0, x prime is the variable in lambda in the Lagrangian subspace. And you can split this subspace into one real component and a rest. And this rest has the structure of a what's called a Jordan algebra, a cubic Jordan algebra that has a lot of structure theory. In particular, it has a Jordan determinant. That's a cubic polynomial on this complement J here. And that's what you use in your formula. Then you have some exponential factor, which is obviously unitary. So this cubic term divided by lambda times x0. And then you flip these two coordinates. In some sense, for me, these two coordinates don't have anything to do with each other. One is coming from the Lagrangian subspace, and the other one is coming from A. And the action of G, or of this Weyl group element, seems to flip these two unrelated coordinates. But that's the way things work. It's the unique extension. So actually, this the story I told you is doesn't just work for split real reductive groups of type A or D or E, but in higher generality, you can do this over any local field of characteristic non-zero and not equal to 2. Gordon generalized this to G2 a little later, and I think a student of Kazhdan did the same construction for all exceptional p-adic groups. And you have to check a lot of relations for this to work. What's a little striking at this point is if you compare the formulas that you get here, that's what Gordon is doing in his paper with the case of G2 with Gelfand's paper, you get exactly the same formulas. So in some sense, this explains a little bit the formulas that you find in Gelfand's paper. But the formulas also look a lot like the formulas that Torosot has for the double cover of SL3. So probably maybe you can also adapt this construction to type A. And they also have a striking resemblance with this construction by Sabourin or spin 4-3. So there are a few different constructions by different methods, which seem to give the same result, the same type of representation, the same realization. So questions are, the first question, where does this action of this Weyl group element come from? How can one give maybe a more intrinsic explanation of this formula? And the second question is, if it works in this generality and it works in a lot high generality for exceptional p-adic groups, I think Rumelard actually writes that with some modifications of his construction, you could do the same thing for real groups. Can this construction be generalized to a lot of real groups? So that's the questions I asked myself. And here's an alternative approach to the construction. So since the model is very explicit, you can, without a lot of work, find a p-equivariant functional on the smooth vectors. So you find a distribution vector which transforms under the parabolic subgroup P in a certain way by a character. And this means that the representation sits inside a certain degenerate principal series induced from this character chi. And of course, so what Kazhdan-Savin did, they constructed the representation by their method, then realized that they can be embedded into a principal series. But you can also start the other way around and say, I want to construct this representation inside a principal series, because this will give you this action of the Weyl group element for free. It comes from the principal series action. And also this construction might generalize to other groups because the degenerate principal series construction is very robust. But there are certain difficulties here. The first one is, of course, it sits in there as a subrepresentation, and that's usually a difficult problem describing what the invariant irreducible subrepresentations of a principal series are explicitly. Usually one describes them in terms of images or kernels of intertwining, standard intertwining operators. But in some sense, it might be difficult to write down even a single function in this image of the intertwining operator and the kernel. The second problem, since we're concerned with unitary representations, is what's the invariant inner product on such a subrepresentation of a principal series? It's also a difficult question in general I mean, even in the classification of the unitary dual, that's one of the key problems. Of course, you can write down an invariant Hermitian form coming from these intertwining operators, but it's difficult to decide when it's positive definite. It's given by a singular integral kernel, and we know that the construction by Gordon and Kazhdan gives an L2 model. So what do these two things have to do with each other? So what I'd like to do in this talk today is start with a different construction and a different construction of minimal representations, and take that as an idea for this case where we have a parabolic subgroup with Heisenberg new radical. Let's start with a construction of minimal representations coming from Siegel parabolic subgroups. So G more or less be in the same category of groups, for simplicity simply connected. And now we start with a maximal parabolic subgroup which has an abelian unipotent radical. So in that sense, the parabolic subgroup is easier. It's often referred to as a Siegel parabolic subgroup. And you form the corresponding degenerate principal series representations. And for simplicity, let's just induce from a character of M here. Then you have a character of A, parameterized by more or less one complex number because A is one-dimensional. So you get this family of principal series representations, which are unitary on the imaginary axis and non-unitary. Could be unitarizable otherwise, but that's more difficult. And the question of when these representations, so generically for generic lambda, they will be irreducible, but the interesting representations arrive at reducibility points. So for which lambda is this representation reducible? What's the composition series? Which of the composition factors are unitary? That's a question that was studied a lot in the 90s, initiated by or I think more or less by Sahi, who did a lot of cases and then some follow-up work. And I think now we have a complete picture of all these in a degenerate principal series and their composition factors and unitarity. These are mostly algebraic methods that you apply. You look at k-types, you look in which way you can step from one k-type to the next k-type. You can look at eigenvalues of standard intertwining operators. So that's very algebraic. But from these algebraic considerations, you find that the minimal representation actually occurs, maybe not for all groups, maybe not for all parameters, but it occurs in a lot of cases as a subrepresentation. You can maybe see this from the k-type picture. So the problem is, how can I describe it as a subrepresentation, and how can I describe the invariant inner product? How can I get a model for this representation? And here's a viewpoint that's usually not written like this in the literature, but I think that's what happens. So you realize your representation as functions on the opposite unipotent radical by restricting. So principal series means sections of a line bundle over G mod P. Inside G mod P, you have the open dense Breuer cell, let's say the opposite unipotent radical. That's an abelian Lie group, unipotent, so it's basically a vector space. And you realize this representation on functions on this vector space by restricting to this n bar. And you get something that's between Schwarz functions and smooth functions. And with a certain decay property at infinity given by this parameter lambda. Now you want to find some subrepresentation in here and its functions on a vector space. And in this case, this vector space has more structure coming from this the fact that it's the unipotent radical of a parabolic subgroup. Has the structure of such a Jordan algebra. I don't want to talk so much about the structure theory here. Let me just say the structure theory gives rise to a certain system of differential equations. I think this is the point where this construction, at least, does not make sense in the p-adic world anymore, where you might have to make some adjustments if you want to make this work for p-adic groups. So you find a set of differential operators, and these differential operators, this family of differential operators is of order 2, constant coefficient differential operators, and they are what's called conformally invariant for the representation for one particular parameter lambda of the principal series. And this means, as an algebraic relation, if you take the commutator with some Lie algebra element acting in this representation and such a second order operator, you get a linear combination of these operators again with some coefficients, which could be functions also. But the point is that this relation, this algebraic relation, will tell you that the kernel, the joint kernel of all these operators, will be a subrepresentation. You can describe the subrepresentation as a kernel of a system of differential operators. To get a feeling for what kind of operators occur, let me show you 2 examples. One is the typical example of the symplectic group or metaplectic group, where you expect to find the metaplectic representation as the minimal representation. And I think Toshi indicated this in in the lecture this morning. The unipotent radical of the Siegel parabolic is just symmetric matrices, n by n symmetric matrices over the reals. And these differential operators can be chosen to be all the 2 by 2 minors of, for instance, the gradient. So you plug in the partial derivatives in your entries, and you take 2 by 2 minors. That's a second order operator with constant coefficients. And the system satisfies this algebraic relation. The other example also mentioned in this morning's talk is indefinite orthogonal groups, where you also have such a Siegel type parabolic subgroup. The new radical here is r to the p plus q. It should be viewed as a quadratic space with a quadratic form of signature p comma q. And the corresponding wave operator, here you can do with a single differential operator, is conformally invariant for this system. That's something that was shown by Kobayashi and Mano in their work. So the kernel of this operator, that's now the general observation. The kernel of the system of differential operators is a subrepresentation. That's exactly this algebraic relation up here. So you find a subrepresentation, and that will be your minimum representation. But of course, it's difficult to understand the kernel of a differential operator, or of a system of differential operators. It's difficult to even write down a single solution in general to this system. The second problem is, or the second difficulty is to write down an inner product on this subspace that's invariant. You can again take the standard intertwining operators, and this gives you an expression of this type as a convolution operator in the first function u here, and then you take the standard pairing with the second function v on this vector space. But again, sometimes you have to regularize this one in the parameter lambda. This is also not so clear to see whether this one is positive definite or not. But now the key idea in this context, and that goes probably back to Rossi and Vernier already for holomorphic discrete series, is if you have a constant coefficient differential operator, this is easy on the Fourier transform side. Take the Euclidean Fourier transform, and the constant coefficient differential operator becomes a multiplication operator. And the same goes for this convolution here. If you have a convolution and on this vector space, on the Euclidean vector space, the Fourier transform will turn this convolution into a multiplication operator. So the idea is to apply the Fourier transform in this context and maybe get an easier realization, and that's exactly what's happening. So the Euclidean Fourier transform can be applied here, and it provides a new realization of this subrepresentation of which is the kernel of this differential operator. And as I said, these differential equations will turn into multiplication equations. And if you have a distribution, this will in general be a distribution, which multiplied by a certain polynomial is 0. This means that the support of this distribution is on the 0 set of that polynomial. So on the Fourier transform side, you expect your subrepresentation to consist of distributions supported on some subvariety, submanifold. The convolution from the possible inner product or Hermitian form turns into a multiplication, and this is where you see some kind of L2 inner product, and that's exactly what's happening. So Rossi Vernier did this for, they didn't talk about differential operators, I think, but they did the construction for the holomorphic discrete series and its analytic continuation, and then this was again continued by several people to now cover all the cases of Siegel parabolic subgroups. You have to exclude some cases which do not have a minimum representation, and some cases where this construction doesn't work. But in all the other cases, you'll find that this Fourier transform actually gives you a realization of the minimum representation. And on the other side, you exactly get an L2 space on a subvariety, which is the 0 set of all these symbols of your differential operators. For example, in the case that Toshi discussed this morning, this is the cone, because it's the 0 set of the quadratic form. In the symplectic or metaplectic case, you take the 0 set of all 2 by 2 minors. This gives you the rank 1 matrices in symmetric groups, and that's more or less where your metaplectic representation lives. And you have a certain measure here, and it's exactly in an L2 model. And you can check that the Lie algebra is indeed acting by, it's already acting on here by differential operators with polynomial coefficients, and then of course this turns to differential operators with polynomial coefficients on the other side by the Fourier transform. So you get exactly such an L2 model for all these representations. for the metaplectic representation, for the minimal representation of OPQ, and a lot of other cases. So the idea to maybe explain these representations constructed by Gordon and Kazhdan is to do a similar construction, but now for the principal series induced from such a Heisenberg parabolic subgroup. Sure.
So yes, in general, this radical line is a Jordan algebra. So in general, this polynomial is just 2 by 2 minors, right?
Right.
And these polynomials you're talking about, they're always just 2 by 2 minors, right?
In the case of matrix, whether Jordan algebra is a matrix.
Jordan algebra, right?
You have these rank 2 Jordan algebras, like the one here. But in all the other cases, they are 2 by 2 minors. Yeah. So the program for the rest of the talk is I'd like to explain how one can generalize all these steps to Heisenberg parabolic subgroups and obtain a similar construction. Yeah. So start with a simple real group which possesses a parabolic subgroup which has a Heisenberg unipotent radical. So it's a Heisenberg group. And you can in the same way define the degenerate principal series inducing from a character of M and a character of A. And in this case, it's known by works of different people that the minimal representation can be found in as the kernel of some differential operators, and then take some kind of Fourier transform to find an L2 model. Again, as in the case of the Siegel parabolic subgroup, you realize your representations on this Heisenberg group n bar, or in functions on the Heisenberg group. And then the idea is to use the structure of this Heisenberg group to describe the ingredients, the differential operators that should give you as kernel the subrepresentation, the standard intertwining operators, which are relevant for your inner product, and the Fourier transform, which should give you the L2 realization. So for this, you need a little bit of structure theory. Just the fact that it's a the unipotent radical is a Heisenberg group is not enough. This doesn't give you any way of constructing canonical differential operators, but you do have more structure. This unipotent radical occurs inside a simple group. So on the Lie algebra level, you see this in terms of a so-called 5 grading. You have a grading, you take this step. You have a grading operator H, that's an element in the middle part here. That's the generator of A of your A in the parabolic. And this is acting by the adjoint representation in a diagonal way, has eigenvalues -2 up to +2. The 0 eigenspace is exactly the Lie algebra of the Levy of the parabolic subgroup. And the G1 plus G2 is N, and G-1 plus G-2 is N bar. And you see the structure of the Heisenberg group or the Heisenberg Lie algebra. G2 is the center, and the bracket of G1 with G1 gives you G2. So to start the structure theory, you can complete this H, this grading element in the middle to an SL2 triple by taking something from G2 and G-2. In this case, I assume it's a Heisenberg group. So the center is one-dimensional, G2 and G-2 are one-dimensional. So more or less in a unique way, you can complete this to an SL2 triple. And now this SL2 triple allows you to define some more structure. First of all, of course, since this is a Heisenberg group or Lie algebra, this G-1 should be a symplectic vector space, and the symplectic form is given by the Lie bracket more or less. So the Lie bracket of 2 elements in here end up in G-2, which is generated by F. This is scalar times F, and that's exactly your symplectic form. But you get more structure. For example, the M is acting in a symplectic way on this vector space, symplectic vector space G-1. So it can be viewed as a subalgebra of the symplectic group, symplectic Lie algebra. And then you can do a little more. You can associate some symplectic invariants with this construction. And what you do is you start with an element X in G-1, the symplectic vector space, and you apply the adjoint representation of this element to G2, so to this element E, the generator of G2. If you apply it once, it's in the piece G-1, you step down by 1. So you end up in G1. This is more or less the isomorphism between G-1 and G1. It's not so interesting. But if you apply twice, if you take the square, you end up in G0, and you can show you actually end up in M. You end up in the symplectic Lie algebra. And that's kind of a moment map. You map from the symplectic vector space to the Lie algebra of M, which is acting symplectically. The quadratic map, because it's you have the square here, quadratic polynomial map, which plays the role of a moment map. And you can, of course, iterate this. You can apply X once more. Then you end up in G-1. So this gives you a self map from V to V, which is cubic polynomial. And if you do it once more, you end up in G-2. You get a multiple of multiple of F, which is the generator of G-2. And if you do this 5 times, you end up in G-3, which is 0. So you get these invariants. And in some sense, taking the vector space with a symplectic form, the Lie algebra acting symplectically, and this moment map, you can reconstruct the Lie algebra. It's a construction by Faulkner, and I learned this from Bob Stanton when I was at Ohio State. And this is the structure theory that needs you, that's getting you going to construct all the necessary ingredients for minimal representations. So, and the first step has already been done. This is a construction by Barchini, Kable, and Zierau. They basically take all these 3 symplectic invariants and quantize them. So in some sense, what you do is you take this polynomial on the symplectic vector space, and you plug in, instead of the variables, you plug in the left invariant differential operators on the Heisenberg group or Lie algebra. This way you get a system of 2nd order differential operators, of 3rd order differential operators, and the single 4th order operator. And these play the role of these conformally invariant operators. Because what Barchini, Kable, and Zierau show is actually for each of those systems that they are conformally invariant in the same way as the family of differential operators that I discussed before in the Siegel parabolic case. I only formulated this for the operators of order 2 here, because that's the one that is relevant for minimal representations. So this system is conformally invariant for some fixed parameter lambda of the principal series. And this, again, this means that the joint kernel of these guys is a subrepresentation. You find a subrepresentation, and that's your candidate for the minimal representation sitting inside this principal series. It could be 0. It could be that the differential equations are too much to ask, and you don't actually get any solution in there. In some cases, and this is written in the paper of Gross and Wallach about the analytic continuation of the quaternionic discrete series. Kable worked out some other cases, and recently Kubo and Ørsted looked at the double cover of SL3 and made this explicit. So these are mostly algebraic methods that tell you that this kernel of this 2nd order system is actually the minimal representation in some cases. So there's a good chance. What's missing is the explicit Hilbert space, the explicit inner product. That's where the Fourier transform comes into the picture. I'm actually cheating a little bit in the statement here to make it a little easier. You have to be aware that this Levy part M could be semi-simple or even reductive, non-simple. If it's simple, the statement is correct. If it's non-simple, in some sense, you get a conformally invariant system for each of the simple or abelian ideals that show up in M. And for each of these ideals, you have maybe a different parameter of the principal series where you can do this construction. But maybe it's for the purpose of the talk, it might be sufficient to maybe assume that M is simple, then it's okay. So now I want to take a Fourier transform of this subrepresentation that has the potential to be the minimal representation. What kind of Fourier transform? Well, the differential operators here are not constant coefficient. They come from left invariant differential operators on the Heisenberg group. So they're left invariant for the action of the Heisenberg group. And the G invariant Hermitian form that has the potential to be the inner product on this subrepresentation is given again by intertwining operators. So there's a convolution involved here. And this is now not the convolution or this one as a vector space, but as a Heisenberg group. So it's the Heisenberg group convolution. So it's both the Heisenberg group structure involved in the invariance of the differential operators and in the formulation of the inner product. So what you should do is take the Heisenberg group Fourier transform instead of Euclidean Fourier transform. Now a quick recap of this group Fourier transform for the Heisenberg group. you parameterize your infinite dimensional representations, irreducible unitary representations of the Heisenberg group by their central character. This is the parameter lambda. This is a variable in R cross, which parameterizes the non-trivial characters of the center. And they can all be realized on L2 of a Lagrangian submanifold. This is the same one you see in Kazhdan-Savin's construction. So you realize these representations on L2 of lambda. And then the Heisenberg group Fourier transform is initially defined for L2 functions on the Heisenberg group, where you integrate your for L1 functions, where you integrate your L1 functions against the representation. So you get an endomorphism of this linear map on this space of L2 functions. For each, and this map depends on the central character lambda. And this is important because in some sense you see, you count the number of variables. The Heisenberg group has like 2n+1 variables, 2n coming from the symplectic vector space, 1 from the center. This one variable from the center can be seen here. That's the central character. And the 2n variables are kind of hidden here. Something from L2 of Rn to L2 of Rn. Of course, this is a little more complicated to study than the Euclidean Fourier transform due to the non-commutativity of the Heisenberg group. And this is somehow reflected on the right-hand side here by the non-commutativity of this endomorphisms of L2 of lambda. Properties, in some sense, it's exactly what we need. It turns convolution into multiplication, now non-commutative multiplication in this endomorphisms, and left invariant vector fields into action, like left action in the Heisenberg representation, in the oscillator representation. L1 is not enough as the domain for this Fourier transform, because if you look at the point where you're supposed to have the minimal representation as a subrepresentation, these are not given by L1 functions on the Heisenberg group, but have some weaker growth properties. So you need to extend this. And the general theory tells you can extend to L2, which is maybe a little better. I mean, it's not larger than L1, but there's a non-trivial overlap. You can extend to L2, and there you get an isometric isomorphism between L2 of the Heisenberg group and L2 functions on this central character with values in the Hilbert space of Hilbert-Schmidt operators on this Hilbert space L2 of lambda. And you have to adjust the measure a little bit. But you need to extend this even more to maybe tempered functions. So the ideal thing would be to extend this to some map on tempered distributions. This turns out to be difficult because in some sense you disregard the finite dimensional representations of the Heisenberg group here. You're only taking the infinite dimensional ones into account. So this might create problems here. In the range where we add, if your parameter for the principal series is in a certain range, then these functions do not decay or do not grow too badly in the principal series. And in that case, you can extend this to at least an embedding into some space of some enlarged space on the right-hand side. And this has to be interpreted in the following way. Here you have functions, or your operators depend on the central variable. This has to be replaced by a distribution in the central variable. And the Hilbert-Schmidt operators from L2 to L2 have to be replaced by operators from the smooth vectors, which is Schwartz functions, into the tempered distributions on the Lagrangian subspace. So this sits inside the one down here, and the one down here is strictly larger. So you get an embedding. You can extend this Heisenberg group Fourier transform in this context, and that way you can move your representation over to the other side. But what is the representation on the other side? The first thing you need to understand is what does this equation, this differential equation that you want to solve, mean on the other side? So what's the Fourier transform of this equation? That's the first computation you have to make. This turns out to be, so this system of differential operators is parameterized by T, which is an element of M. M sits in the symplectic Lie algebra. And on the other side, it means you compose your operator with the metaplectic representation applied to T. In some sense, you look at the metaplectic representation restricted to M on the other side. That's not so difficult a computation, but now you want to solve the equation, this one's equal to 0. This means this guy is equal to 0 for our lambda. So the image of this operator is in the kernel of that one. You need to find the kernel of these guys for all t. And this means you need to find m distinguished vectors in the metaplectic representation. And that's where you have to work a little harder. We can show that these that m is in some sense large enough inside the symplectic or metaplectic group that there's a unique, that's again cheating, that's two-dimensional, but there's only one of them is relevant for this construction. So essentially you only get one m distinguished vector here. And this tells you that, that the image of this guy has to be a multiple of that vector. I'm cheating a little more because in these two classical cases, you have to adapt the construction a little bit due to the fact that m is not simple, but you can treat it in the same, along the same lines, but you have to adjust the construction. Now, what I said, if this one is equal to 0 for all t, then the image of this one has to be in the kernel of the metaplectic representation, which is one-dimensional, so it's multiple of psi. And this is somehow where you lose the commutativity of the non-commutativity of the Heisenberg group Fourier transform, because now you end up in a one-dimensional space on the image. You have a rank 1 operator, and a rank 1 operator is given by the projection. So it's given by mapping an element phi in the Schwarz space to a multiple of psi, and this multiple is given by testing phi against some distribution that could depend on lambda. So this is crucial. You show that your system of differential equations on the one side, defining the subrepresentation, corresponds on the other side to reducing your variables. You've somehow gotten rid of one copy of this S prime on the other side. It's because you have the fixed psi here. So you get a map from the kernel of these of this system of operators to, which is now a distribution in the central variable, central character of the Heisenberg, and some temper distribution on lambda. So you can move your representation over to that side, and you get a new realization of this representation on the Fourier transformed side on some subspace of distributions in the central character variable and the Lagrangian. And this again could be 0, and that's where you have to work a little harder again. When is this non-zero, and how can you express the invariant inner product? So first thing is you compute the Lie algebra representation on the Fourier transform side. That's a longer computation. But the nice thing is it can be expressed completely in classification-free way in terms of explicit formulas, only using these 3 symplectic invariants. That makes it possible to compute in all these exceptional cases without having to compute with the exceptional groups, but only using some symplectic formulas for the moment map and this cubic map and so on. And you find that your Lie algebra acts by differential operators of order at most 3. And then you have to show that you actually get a unitary representation on that side, and it's exactly on an L2 space. So although a priori you get distributions on here, you can show you get L2 functions, and the invariant inner product is exactly the L2 inner product, maybe with some weight factor here, but that's not so important. Exclude some cases which do not have a minimal representation, and also have to exclude F4 for different reasons. So that's the way you get the minimal representation. And one key part of the proof of the construction here is that you compute explicitly on the Fourier transform side using these explicit differential operators describing the Lie algebra action, the lowest k-type. So for all these realizations of minimal representations, you have explicit formulas for the lowest k-type. In some cases, they are spherical. That's where you recover these formulas by Kazhdan, Piolin, and Waldron for the spherical vector. But in general, they are not, and you have non-trivial lowest k-types. And for those, you get explicit formulas. Now, this is exactly what we wanted, because if you compare these formulas up to maybe a change of coordinates that removes this weight factor in the L2 space here, you get exactly the formulas that come out of the construction by Kazhdan-Savin that you can find in Gelfand's work and also in Torasso's construction. In some sense, this gives you a way of uniformly constructing these representations, and you obtain all the same formulas. And also, by the construction, you also get a formula for this Weyl group element, and you can actually compute that formula. And looking at it from the other side of the ocean, you can say I could also have taken this formula that I get out of this one here and used the same construction as Gordon and Kazhdan did. But it's something that comes out of the construction here. So it's known in a lot of cases, but there's also a few cases in which, at least to my knowledge, this construction is not known for most of the indefinite orthogonal groups and for the quaternionic real forms of exceptional groups of type E. You got these new models. So to conclude, a few questions and open problems here. I described two constructions to you, one using the Siegel parabolic subgroup and one using the Heisenberg parabolic subgroup. And some of the groups that occur in this construction actually have both. So in some sense, you get two different models of minimal representations, both on an L2 space, and you could ask, how are they related? Can I construct an intertwining operator from one side to the other side? Does this have maybe nice properties, nice applications to analysis? Second question is, you also have other constructions of minimal representations, of course, one of them by Brylinski and Kazhdan, which should be viewed as a realization on holomorphic functions or sections on some object. That's a nilpotent KC orbit in PC. And this can be viewed as a kind of Fock model for the metaplectic representation. And here you have a Schrödinger model. And these two models are usually related by a kind of a Bachmann, Siegel-Bachmann type transform. Is there something similar here? And the last thing, picking up the theme of the conference, there are a few nice subgroups. I think a dual pair here. You take the Levy M of your parabolic and take the SL2 that's sitting, I think I constructed this SL2 triple E, F, and H. They form a dual pair inside all these groups. What's the restriction to this dual pair? Can you maybe use the L2 model in the known cases or in the new cases to put up a dual pair correspondence? And maybe the new thing here is that the Lie algebra representation is now very explicit. It might help to understand some of these restrictions. That's what I wanted to say. Thanks for listening and happy birthday, Gordon.